There are several possible reasons why two Y-connected three-phase secondary feeds from three single-phase transformers would be connected to the same main distribution panel, or MDP, in the same building. Firstly, redundancy and reliability may be the primary driver. Having two separate transformer banks provides redundancy in case one transformer fails. This ensures a more reliable power supply to critical loads within the facility. Should one transformer bank experience an outage, the other can continue to supply power, minimizing downtime. Secondly, load balancing is another important consideration. If the facility has a heavy electrical load, the two transformer banks can be used to balance the load more effectively. This reduces stress on individual transformers and improves overall system efficiency. By distributing the load across multiple transformers, the system can operate more efficiently and reliably. Thirdly, voltage regulation plays a role. Single-phase transformers are more susceptible to voltage fluctuations than three-phase transformers. By connecting two single-phase transformers in a Y configuration, the voltage fluctuations can be minimized, providing a more stable voltage supply to the MDP. This is particularly important for sensitive electronic equipment that requires a stable voltage supply. Fourthly, isolation could be a factor. In some cases, the two transformer banks may be used to isolate different sections of the facility. This can be beneficial for safety purposes or to prevent interference between different electrical systems. For example, one transformer bank might supply power to critical systems, while the other supplies power to non-critical systems. Fifthly, cost optimization may be a reason. Using three single-phase transformers instead of a single three-phase transformer can sometimes be more cost-effective, especially if there is a limited available space or budget constraints. Single-phase transformers are often less expensive and easier to install than three-phase transformers. Sixthly, maintenance considerations come into play. Single-phase transformers are typically easier and less expensive to maintain than three-phase transformers. By using multiple single-phase transformers, the facility can minimize maintenance downtime and costs. Maintenance can be performed on one transformer bank while the other continues to supply power. Seventhly, future expansion is something to think about. If the facility is expected to expand in the future, the additional transformer bank can provide additional capacity and flexibility for future electrical load increases. This allows the facility to easily accommodate future growth without having to replace the existing transformer infrastructure. It's important to note that this type of configuration is not commonly used and may not be the most efficient or cost-effective solution for all facilities. The specific reasons for this configuration should be determined by a qualified electrical engineer based on the facility's specific needs and constraints. Engineers would typically look into various factors, including the facility's load profile, criticality of loads, space limitations, budget constraints, and future expansion plans to determine the best transformer configuration for the facility. Let's delve a bit deeper into each of these reasons, providing more technical details. When discussing redundancy and reliability, it's crucial to understand how this configuration enhances the overall system resilience. In a typical scenario with a single three-phase transformer, a failure of that transformer would result in a complete power outage for the entire facility. However, with two separate transformer banks, the failure of one bank only affects a portion of the load, while the other bank continues to supply power. This allows critical systems, such as emergency lighting, life safety equipment, and critical IT infrastructure, to remain operational during the outage. The load balancing aspect is also more complex than it initially appears. It's not just about dividing the total load equally between the two transformer banks. Engineers must carefully analyze the facility's load profile to determine the optimal distribution of loads. This involves considering the types of loads, their operating characteristics, and their impact on the transformer's performance. For example, some loads may be highly inductive, while others may be highly capacitive. These types of loads can cause voltage imbalances and harmonic distortion, which can negatively affect the transformer's performance and lifespan. By carefully balancing the loads, engineers can minimize these effects and improve the overall system efficiency. Voltage regulation is another area where this configuration can provide significant benefits. Single-phase transformers are more susceptible to voltage drops than three-phase transformers, especially under heavy load conditions. This is due to the higher impedance of single-phase transformers compared to three-phase transformers. By connecting two single-phase transformers in a Y configuration, the voltage drops can be minimized, resulting in a more stable voltage supply to the MDP. This is particularly important for sensitive electronic equipment that requires a stable voltage supply to operate correctly. Voltage fluctuations can cause malfunctions, data loss, and even permanent damage to sensitive equipment. Isolation, as mentioned earlier, can be used for various purposes. In addition to safety and interference prevention, isolation can also be used to protect critical systems from voltage surges and other electrical disturbances. By isolating different sections of the facility, engineers can prevent these disturbances from propagating throughout the entire system. For example, one transformer bank might supply power to a data center, while the other supplies power to a manufacturing area. This prevents any electrical disturbances in the manufacturing area from affecting the data center's sensitive equipment. Cost optimization is a complex topic that involves considering various factors, such as the initial cost of the transformers, installation costs, maintenance costs, and operating costs. In some cases, using three single-phase transformers may be more cost-effective than using a single three-phase transformer, especially if there are space limitations or budget constraints. Single-phase transformers are often smaller and lighter than three-phase transformers, which can make them easier and less expensive to install. They are also typically less expensive to purchase and maintain. However, it's important to consider the operating costs as well. Single-phase transformers may be less efficient than three-phase transformers, which can result in higher energy bills over the long term. Maintenance considerations also play a significant role in the decision-making process. Single-phase transformers are typically easier and less expensive to maintain than three-phase transformers. This is because they have fewer components and are less complex in design. Maintenance can be performed on one transformer bank while the other continues to supply power, minimizing downtime. This can be a significant advantage for facilities that require a continuous power supply. Future expansion is another important factor to consider. If the facility is expected to expand in the future, the additional transformer bank can provide additional capacity and flexibility for future electrical load increases. This allows the facility to easily accommodate future growth without having to replace the existing transformer infrastructure. The additional transformer bank can also be used to supply power to new areas of the facility or to support new equipment. In addition to these reasons, there may be other factors that influence the decision to use two Y-connected three-phase secondary feeds from three single-phase transformers. These factors may include the availability of transformers, the local utilities requirements, and the facility's specific operating conditions. It's important to consult with a qualified electrical engineer to determine the best transformer configuration for a particular facility. The engineer will be able to assess the facility's specific needs and constraints, and recommend the most efficient and cost-effective solution. It is also worth noting that the NEC, or National Electrical Code, provides guidelines for the installation and operation of transformers. These guidelines are designed to ensure the safety and reliability of electrical systems. Engineers must comply with the NEC when designing and installing transformer systems. The NEC covers various aspects of transformer installation, including sizing, protection, grounding, and ventilation. For example, NEC Section 450.3 provides requirements for transformer overcurrent protection, while NEC Section 450.13 provides requirements for transformer grounding. NEC Article 450 provides comprehensive guidelines for transformers. When dealing with transformer installations, it's essential to consider various factors to ensure safety, efficiency, and compliance with electrical codes. Here is a breakdown of key considerations. 1. Transformer sizing. Selecting the appropriate transformer size is crucial for meeting the load demands of the facility without overloading the transformer. Factors to consider include the connected load, anticipated future load growth, and the transformer's continuous load rating. 2. Overcurrent protection. Adequate overcurrent protection is essential to safeguard the transformer and connected equipment from damage due to faults or overloads. Fuses or circuit breakers should be selected and sized according to NEC guidelines to provide reliable protection. 3. Grounding. Proper grounding of the transformer and associated equipment is critical for personnel safety and to minimize the risk of electrical shock. Grounding electrodes, grounding conductors, and bonding connections should be installed in accordance with NEC requirements. 4. Ventilation. Transformers generate heat during operation, so adequate ventilation is necessary to prevent overheating and ensure efficient cooling. Ventilation openings should be sized and located to provide sufficient airflow around the transformer. 5. Location. The location of the transformer should be carefully considered to minimize potential hazards and ensure accessibility for maintenance. Transformers should be installed in dry, well-ventilated areas away from combustible materials. 6. Wiring methods. Proper wiring methods should be employed for connecting the transformer to the power source and load. Conductors should be sized according to NEC ampacity tables and installed in approved raceways or cable trays. 7. Disconnecting means. A disconnecting means should be provided to isolate the transformer from the power source for maintenance or emergency purposes. The disconnecting means should be readily accessible and clearly labeled. 8. Signage. Appropriate signage should be installed to identify the transformer and provide important information such as voltage ratings, kVA rating, and emergency contact information. 9. Compliance with codes and standards. All transformer installations must comply with applicable electrical codes and standards, including the NEC, ANSI standards, and local regulations. 10. Regular maintenance. Regular maintenance is essential to ensure the reliable operation and longevity of the transformer. Maintenance activities may include visual inspections, insulation testing, oil sampling, and cleaning. Let's talk about transformer efficiency. Transformer efficiency is a critical parameter that indicates how effectively a transformer converts electrical energy from the primary side to the secondary side. It is defined as the ratio of output power to input power, expressed as a percentage. Higher efficiency transformers minimize energy losses, reduce operating costs, and contribute to a more sustainable electrical system. Transformer efficiency is influenced by several factors, including core material, winding design, load level, and operating temperature. Core losses, also known as iron losses, occur in the transformer's core due to hysteresis and eddy current effects. These losses are dependent on the core material and the frequency of the applied voltage. Winding losses, also known as copper losses, occur in the transformer's windings due to the resistance of the conductors. These losses are proportional to the square of the current flowing through the windings. Load level affects transformer efficiency because core losses remain relatively constant regardless of the load, while winding losses increase with the square of the load current. At light loads, core losses dominate, resulting in lower efficiency. As the load increases, winding losses become more significant, leading to a decrease in efficiency at very high loads. Operating temperature affects transformer efficiency because the resistance of the windings increases with temperature, leading to higher winding losses. Transformer manufacturers provide efficiency curves that show how efficiency varies with load level. These curves can be used to select the most efficient transformer for a given application. High-efficiency transformers are designed to minimize energy losses and improve overall system performance. These transformers typically feature advanced core materials, optimized winding designs, and efficient cooling systems. Investing in high-efficiency transformers can result in significant energy savings over the transformer's lifespan, reducing operating costs and environmental impact. Energy-efficient transformers often meet or exceed industry standards, such as those established by the National Electrical Manufacturers Association, or NEMA, and the Department of Energy, or DOE. These standards specify minimum efficiency requirements for different types of transformers. In addition to efficiency, power quality is another important consideration in transformer installations. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, and harmonic content. Transformers can affect power quality by introducing voltage drops, harmonic distortion, and other disturbances into the electrical system. Voltage drops occur when the transformer's impedance causes a reduction in voltage at the secondary side under load conditions. Excessive voltage drops can cause equipment malfunctions and reduce system performance. Harmonic distortion is caused by nonlinear loads such as electronic devices and adjustable speed drives, which draw non-sinusoidal currents from the power supply. These currents create harmonic voltages and currents that can distort the voltage waveform and cause problems with sensitive equipment. Transformers can contribute to harmonic distortion by amplifying harmonic currents generated by nonlinear loads. To mitigate power quality problems, engineers can use various techniques such as oversizing transformers, installing harmonic filters, and using power factor correction equipment. Oversizing transformers can reduce voltage drops and improve voltage regulation. Harmonic filters can reduce harmonic distortion by filtering out unwanted harmonic currents. Power factor correction equipment can improve the power factor of the electrical system, reducing current flow and improving efficiency. Monitoring power quality is essential to identify and address potential problems. Power quality analyzers can be used to measure voltage, current, frequency, and harmonic content. This data can be used to identify sources of power quality problems and implement appropriate solutions. In summary, using two Y-connected three-phase secondary feeds from three single-phase transformers to a single main distribution panel is not a typical configuration. There may be several reasons for doing so, including redundancy, load balancing, voltage regulation, isolation, cost optimization, maintenance considerations, and future expansion. However, it's important to note that this configuration is not always the most efficient or cost-effective solution. The specific reasons for this configuration should be determined by a qualified electrical engineer based on the facility's specific needs and constraints. Always consult with a qualified professional to ensure the safety and reliability of electrical systems.